Hello, hello, hello. This is section 4.3 in chapter 4 about functions, and this section is about nonlinear functions, so patterns and nonlinear functions. So what do we do with nonlinear functions? How are they different than linear functions? So the goal to write down right now, I can identify and represent nonlinear functions. So far we've done looking for linear and representing linear functions. We're going to do the same thing with nonlinear functions today. So to start us off, a couple of vocab words. One we've done already. The first one is a linear function. And a linear function we've talked about is a function whose graph is a non-vertical line um, or part of a non-vertical line. So if we look at all these, they're all slightly different, but if it was a vertical line going up and down, that would not be a function, so that's why it's not a linear function. But these are all linear functions because they're all non-vertical lines. So when we graph, the other one is a nonlinear function. And a nonlinear function is a function whose graph is not a line or part of a line. So when you look at the graph of a nonlinear function, there's many different ways that it could look. And the ones we've got here, this is actually called a parabola. It's got a little curve to it, kind of looks like a U. This one right here kind of looks like well, kind of some sort of an S, but this is nonlinear. It's got some curve to it. Even this one on the far right, this is an absolute value function. They look like it's made up of two lines, okay, but it is not. But they're connected, and this makes a V. This is a nonlinear function, okay? Just a linear function is just a line or a part of a line. This would be more than that, so this is nonlinear, okay? So those are our two key vocab words for today. The new one is the nonlinear. All right, so here's something worth reading. It says essential understanding. Just like linear functions, nonlinear functions can be represented using words, tables, equations, sets of ordered pairs, and graphs. So we get the ordered pairs usually from the tables. And we're going to do this today. That's what we're going to work on. So first of all, determining if it's linear or nonlinear is the first part that we want to look at. Oh, what happened there? All right. So this is our first thing. It says the area, A, in square inches of a pizza is a function of its radius. So what it means by that is based on the radius of a pizza. So if you have your pizza, I know you don't usually have a blue pizza, pepperoni's on there, sausage. The radius is always any line from the outside of the circle to the middle of a circle. And it's saying here is the area is based off of whatever the size of the radius is. The cost in dollars of the sauce for pizza is a function of the weight. So depending on the weight, that determines the cost of the sauce. So graph these functions shown. We're going to do two examples at once. So maybe we'll do two examples at once. So we have our graphs already. The first one is the area of a pizza. It says the radius and the area. So this would be your x and your y. That's how we always do it. So if you were to graph that, because graphing them is the best way to tell if it is a function or not, or a linear function or a nonlinear function. So let's graph them and tell whether it is a linear or not. So if you were to graph the one on the left, we have the first order pairs 2 and 12.57. So that would be right about here. Now again, when you're making your graph, you can make the x and y axis numbered how you want, as long as they're going up by the same every time. So if you look at this one, since the x-axis only goes up by 2, the x's only go up by 2 every time, we can keep these normal going up. Each dash is 1, 2, 3, 4. But if you look in the table, the y's, or the area, a lot bigger numbers. So it started here. This is actually going up. Each dash would be 50, 100, 150, 200. So that's so that they can all fit on there. And if you graph it, this is 2 and about 12.57. So it's not the easiest to find on there, but that's about where it is. For 4, it is about 50, so right on this 50 line. For 6, we have 113, so 6 would be 1 and 113. 8 and 201, so just above 200. and then 10 and 3/14, so over 300. If you look at this, this is not a line because it's curved. So it curves. If you connect the dots, it curves, and this graph is a curve, so it is not linear, non-linear. All right. Now let's look at the second one. We have 2 and 80 cents. So 2 ounces of sauce would be 80 cents. So this one is just going up by ones the whole time because we're dealing with small numbers. For 2, it's going to be 80 cents. For 4, it says it's $1.60, so it doubled. For 6, 2.40, so it adds another 80 cents. For 8, 3.20. Now, when you graph it and you connect the dots, you see that this is a line, which means that this would be a linear function. So graphing a function is probably the easiest way to determine if it's linear or not, until you start recognizing some patterns in different equations or tables. This is probably the best way to check if it's linear or not. So let's try that. Why don't you try this one on your own? It says, the table below shows the fraction A of the original area of a piece of paper that it remains after the paper has been cut in half a certain number of times. Graph the function represented by the table. Is the function linear or nonlinear? So this would be your x and this would be your y when you're graphing it. So go ahead and do that and determine if it's linear or nonlinear. Alright, so I made mine here down on the bottom, and I labeled and you can make it, we really only need to use the top right quadrant, and that would be the first quadrant. But I labeled them how I wanted to label them so I could fit. Now I made the x-axis just go up by ones because that's what these do. The y, I made it go up by 1/4 each time. 1/4, 2/4, which would be 1/2, 3/4, and then 4/4 or 1. And then I graphed it. So 1 and 1/2. So 1 over 1/2 up, which is 2/4. 2 over and 1/4 up. 3 over and 1/8, which would be in the middle there. And if you see the graph, at first it looks like maybe it'll be closer to line, but looks like now it's kind of going on a curve, and it would be going like this, which means that this would be non-linear because it does not make a line. Oops. Will the area ever reach 0? I don't think so, because it's going to get closer and closer and get half and half, but it'll never. You can't take half of something and get 0, because if you look at this, it's dividing it by 2 every time. So no, it will not. Alright, going on to the second part of this is patterns of nonlinear functions. So looking at patterns, kind of like we did with linear functions, and representing them a few different ways. So, this problem right here, the table shows the total number of blocks in each figure shown as a function of the number of blocks on one edge. What is the pattern you can use to complete the table? Represent the relationship among, or using words, an equation, and a graph. So let's look at this. 1 block, and the side length would be 1. So then it's also written as an ordered pair over here. Number of blocks on the edge. So, well, I guess so. We have 2 blocks on the edge, and we have 1, 2, 3, 4, 1, 2, 3, 4, and then 4 on the bottom. So it'd be 8 blocks total. For 3 blocks on one edge, it looks like there's 3, 9, 27 total. Whoops. Now you can keep drawing this and draw it so that you have 4 blocks on the edge. But let's see. If you look at this, I think I can see a pattern. And most of this is looking for patterns. Now, if you're looking at it this way, this is just going plus 7, then plus 19. That doesn't look like a good pattern. I don't know what that's going to be. So let's look from what the difference between x and y is. So this would be 0, then 6. This would be 20. That doesn't help me. Maybe multiply. Ooh, I think I found it. What's the relationship between 2 and 8 other than multiplying by 4? This would be 2 cubed, or 2 times itself 3 times would equal to 8. Because then 3 cubed is 27. So I think whatever it is, and 1 cubed is actually equal to 1. So every number, it's just you're cubing it, and that's kind of why it's a cube. So we do 4 cubed, or 4 to the 3rd power. That would be 4 times 4, 16 times 4 would be 64. So our ordered pair would be 4 and 64. 5 cubed would be 125. So that'd be 5 and 125. So the y values are getting big really fast. So let's represent that a few different ways. We have our table then. We filled it in with a table. We can write that in, whoops, we can write that in words and describe how that's changing. And you can say it this way. We have our little thing in words right here. The total number of blocks is the cube of the total number of blocks on one edge. Okay? And you can say a different way too, but if the total number of blocks in the thing would be the number of blocks on one edge times itself 3 times, or cubed, or raised to the third power. So that's the fourth and fifth one right there. An equation where the y is just equal to whatever the x is to the third power. So that's where we have this equation here. And then when you graph them, again, the graph is used. This is every 3. It looks like it's going up to 50. So it's no real specific pattern, but we have it going consistently here. But for 1, you're at 8, so it's really low. 2, or sorry, 1 you're at 1. 2 you're at 8. 3 you're already up to 27, so that's way up here. 4, then you're up to 64, and 5 all the way up to there. So if you connect the dots, and I don't know that it'll ever touch the bottom, but it's a curve. So this one is non-linear. So I'd like you to try this one on your own. Try to figure out the pattern. It says the table shows the number of new branches in each figure of the pattern below. What is a pattern you can use to complete the table? Represent the relationship in words, an equation, and a graph. Alright, so the best way that I could describe that in words was as the figure number increases by 1, the number of branches multiplies by 3. So the number that would be x, and you multiply the y by 3 as you go up. Now an equation, that's a tricky one to write. Multiplying by 3, so if you're thinking of exponents, because that'd be a good thing to think of. 3 is the number that's being multiplied by itself. It starts with 3, and then it's times 3, and then so I believe it would be y equals, let's see if this works, 3 to the x power. So 3 to the first power is 3. 3 to the second power would be 3 squared, or 9. 3 to the third power would be 3 times 3 times 3. So that would work. 3 to the x power, whatever is raised to whatever x is. Alright, now if you graph that, we have 1 and 3. So I labeled it so that you have 1, the x-axis is going up by 1s, the y is actually going up by 25, and then 50, 75, 100. So the first one was 1 and 3, so very small on there, very close to the bottom here. Second one is 2 and 8, so still pretty close to the bottom here. Then it was 3 and 27, so just a little bit above here. Then it was 4 and 81. So getting up here now. Then it was 5 and 243, something like that. So way up here actually. Now if you were to connect those, and you can see right here, that is definitely nonlinear. And it looks like it's got a curve there, so that would be the graph there. We're representing it as a graph. Okay? And the hardest part is usually the equation, but if you can really work towards thinking about what equation would work for these numbers, the better you practice, the better you'll get. So I just want to close it then with one error analysis. So it says a classmate says that the function shown by the table at the right can be represented by this rule, y equals x plus 1. And I want to see if you think that would be correct. It is incorrect. So describe the error and see if you can fix that. So write a new equation, since this one is not correct. All right, and we can talk about that next time. So again, look back at your goal, think about what you learned, identifying and representing nonlinear functions. We'll see you next time.